This morning I got news that my daughter went into labor, so I have no idea if it's going to happen during class. Please excuse me if I get a message during class that my grandson or daughter has been born. I have no idea if it's going to happen. This is not staged. We will see. It may or may not happen. I have no idea. Okay? So we will see. But we do have to do some math. It's a little hard for me to think about right now. But let's go ahead and get going on it. Just like, what is today? Today's Monday. Just like last Friday, we're sort of doing three main things: theory, parametric equations, and the fundamental theorem of calculus. Okay, so we are going to talk more about the increasing function theorem and decreasing function theorem, IFT and DFT. The racetrack principle, which I did assign a problem about. I gave you a key. It's kind of a strange thing to deal with, how to word your proof and that kind of thing, but we'll go over that today. Not sure if we'll get to parametric equations in lecture A. I will try to. I'm going to go pretty quickly over the theory slides. Because then in lecture B, for sure, I want to get to more parametric equations, motion, and the fundamental theorem of calculus. And then it's Thanksgiving break for you guys. So here we go. You ready for some theory here? Okay, we're going to do one of your homework problems, actually, right now, is prove the DFT using the IFT. The IFT we proved, the increasing function theorem we proved with the mean value theorem. But once you've got the increasing function theorem, you can prove the decreasing function theorem using it. Here's a statement of the decreasing function theorem. And there's a typo there. That's supposed to be DFT. Well, I can't fix it on this computer here. Okay. Oh well. DFT, decreasing function theorem, that's supposed to be a DFT. Suppose little f is continuous on a closed interval from A to B and differentiable on the open interval from A to B. If the derivative is always negative for all x in the interval from A to B, again, this symbol means is an element of or is in. This means x is strictly between A and B. Then f is strictly decreasing on the closed interval. So we could prove this with the mean value theorem, but once we know the increasing function theorem, we can also prove it using the increasing function theorem by using a little trick. Some of these things are little tricks to do, okay? This is some ingenuity that's needed. It's not the kind of thing that I would expect you to know how to do on the test. If I do test you on these kinds of proofs, again, I'd probably do it more like a fill in the blank. I would give you the structure of the proof and you might fill in some blanks or maybe ask for reasons for certain steps. But you should strive to understand it. So to prove it, I started off by assuming the same kind of thing that I did with the increasing function theorem proof. Assume you've got two numbers, x1 and x2, in the interval, with one less than the other. And again, it doesn't matter that I assume x1 is less than x2. They're just arbitrary symbols anyway, because I could assume x2 is less than x1. It doesn't really matter. And also because these are arbitrary, our goal is to show that f of x1 is greater than f of x2. Okay, don't be afraid to draw pictures of these kinds of things. So x1 is there, x2 is over here, maybe a is here, and b is here. We've got a function that we want to show is decreasing. The graph is going downward. We better show that f of x1 is higher, greater than f of x2. And again, functions that are not always decreasing can satisfy that kind of property for two particular numbers, x1 and x2, like right there. But they need to satisfy it for all such numbers that satisfy these properties. So it is the fact that these are arbitrary that allows you to finish the proof by showing that inequality. So here's the trick. Like you were told in the book, and I told you on Moodle, let h of x be negative f of x. Just a new function. And the idea is that I'm going to apply the increasing function theorem to h to show it's increasing. The graph of h will be going up. It doesn't have to be above the x-axis. It could be below the x-axis. That would be the graph of h. And then since h of x is the opposite of f of x will be the reflection across the x-axis, something like that. That means f will be decreasing. I'm not trying to draw the pictures perfectly here. F is assumed to be continuous and differentiable on the appropriate intervals, and therefore h will be as well, because it's a constant times f of x. And its derivative will be, by linearity, negative f prime of x. And that is a positive quantity. Because f prime, I'm assuming, is negative, f prime of x. Therefore, negative f prime of x, the opposite of f prime of x, will be positive. Meaning h prime of x will be positive for all x in the interval, and therefore, by the increasing function theorem, we can say h is strictly increasing on the closed interval. Does that really mean f is strictly increasing? Yes, but you really should give reasons. Since h is strictly increasing, that means h of x1 is less than h of x2. Again, x1 is less than x2. H of x1 in this picture is down here. H of x2 is higher. H of x1 is less than h of x2. But what does that mean? It means negative f of x1 is less than negative f of x2, because h is negative f. And then just multiply both sides of this inequality by -1. And you get rid of the negative signs. You also switch this direction of the inequality. Whenever you multiply an inequality by a negative number, it's got to switch its direction. If you're having a hard time believing that, you can try examples with numbers. -5 is less than -3. That's really equivalent to the fact that 5 is bigger than 3. Okay? And that finishes it. Praise the Lord. The proof is done because I have accomplished my goal. You could add another sentence. You could say this means that f is decreasing on the closed interval. Okay, so there's a very logical structure to these things. You need to use what you're assuming. You need to use other facts, perhaps, like the increasing function theorem, what mean value, and that kind of thing. Be careful. Weird things can happen. If you make too many, well, assumptions about things that might seem reasonable, weird things can happen when theorem hypotheses are not precisely satisfied. I've actually shown you this example before, back in chapter 2, I think. For example, there are functions that are differentiable everywhere. They have a derivative everywhere. The slope of the tangent is always defined. Have a positive derivative at a certain number, but are not increasing on any interval about that number, containing that number inside the interval. No matter how small the interval is. You scratch your head and say, well, the derivative is positive, but the function is not increasing. It's positive at just one point we're talking about, not over an interval. This is not contradicting the increasing function here, because I'm only assuming it's positive at one point, at one number. And it makes a difference, because here's a wild example where that's the case. It's a piecewise function. F of x is 1/2 x plus x squared times sine of 1 over x if x is non-zero. And 0 otherwise, if x is 0. Is this really differentiable? Because, I mean, we'd be dividing by 0 there. Well, it turns out it is. F prime happens to equal this. It's 1/2. 1/2 there comes from differentiating 1/2 x plus, now I'm going to use the product rule and the chain rule. 2x is the derivative of x squared, the left function, times the right function, plus the left function, which is x squared, which you don't see here because it ends up canceling, times the derivative of the right function. X squared times the derivative of sine of 1 over x. The derivative of a sine is cosine. We need to use the chain rule. There's a 1 over x in there. Then I need to multiply times the derivative of the inside function. Negative x to the -2. So to get there, this is the same as -1 over x squared. The x squareds cancel, and then you're left with a minus cosine of 1 over x for this term of the derivative. I claim the derivative at 0 is 1/2. I think I won't verify that today, but maybe sometime next week. You might want to think about verifying it yourself. You can't figure that that's 1/2 just by differentiating that. It's not legal, so to speak, because this is undefined right there at 0. I'll let you think about it. But here's what the graphs look like. F of x and its derivative oscillate infinitely often near 0. Remember those examples from chapter 2? F prime certainly oscillates infinitely often, it seems, with a fairly large, relatively constant amplitude. F itself, the blue graph, it does oscillate. You see those ups and downs there? Maybe zoom in with the camera there. There's some little ups and downs there. It actually does oscillate infinitely often because the 1 over x is inside the sine and cosine. As x goes to 0, 1 over x goes to infinity. And you have inputs for the sine and cosine that are cycling over intervals of 2 pi very rapidly. Over intervals of length 2 pi. Here's what it looks like when you zoom in even closer. F of x is oscillating infinitely often. The amplitudes of the oscillations are getting smaller. However, their slopes are not. Their slopes stay relatively large, those oscillations. It's hard to see, but it's true. If you zoom in closer and closer to the origin there, it does look more and more like a straight line with the slope of 1/2. The derivative at 0 is 1/2. But there are ever so tiny little oscillations that you wouldn't even be able to see that are preventing it from actually increasing on any interval near 0. I mean, its derivative is positive and negative on any interval near 0 for that matter. So wild, weird things can happen, okay? If we don't usually worry about these too much in this class, we deal with more ordinary things. But I just want you to realize, theorems are not some trivial thing that, oh, this makes sense, it must be true. You really do need to prove them. It might seem like if the derivative exists everywhere and is positive at a certain number, that means the function's got to be increasing near that number. But that's not true, actually, even though it sounds reasonable. That's the whole point. Weird things can happen. Racetrack principle. Here's the statement. The whole thing. Big long thing. You've got 2 functions now instead of 1 function. And the hypotheses initially are the same as the mean value theorem, the increasing function theorem, the decreasing function theorem, and the constant function theorem. Suppose it's continuous on the closed interval and differentiable on the open interval. The first bullet point says, if the function's value at the left endpoint, a, are the same, if g of a equals h of a, and their derivatives always, and the derivatives always satisfy this inequality up in the top paragraph. I'm assuming that for both bullet points. So g prime is less than or equal to h prime at any value of x. The slope of g is always less than the slope of h at any given value of x. Then g will always be less than h for the first bullet point. On the other hand, if g of b equals h of b, then g of x is always greater than or equal to h of x. In terms of races, horse races say, the first one says if the horses start at the same place at the same time, x is time here. G of a equaling h of a means the position at time a is the same. The faster horse will always be ahead. This assumption up here means g is slower than h. H is the faster horse. So h is always ahead for all x, for all time. You can use a t instead of x. Right? 2 horses start the race at the same place at the same time. They start running. The faster horse is always going to be ahead. Makes intuitive sense. This one's a little harder to understand. But in words it says if they end at the same place at the same time, the horse that is always faster is always behind, actually. And it's catching up at the end. You can think about pictures with these things too. Come over to the board here. In the first bullet point, the 2 values are starting at the same value. G of a equals h of a. And the slope of g is always less than the slope of h. So if g looks like this, h of x for any given value of x has to have a bigger slope. Maybe it looks something like this. Maybe it even does a little oscillation, kind of like that. But there's the visual. That shows you g of x is always less than equal to h of x. It's below it. Mm-hmm.
Is the faster in reference to the actual speed or the change in speed?
To the actual speed. G and h are positions or distances
Yes.
traveled. Their derivatives are speeds. So we're assuming h is faster than g. G is slower than h. They start the race at the same moment at the same time. H is always going to be ahead. On the flip side, if they end the race at the same moment at the same time, same location at the same time, and we're still assuming h is the faster horse, I should probably draw it up higher. So the slope of h has to be higher than the slope of g, then h is going to have to be the lower one. This will be g of x, and this will be h of x in the second loop. Okay? Let's prove the first bullet point using a modified form of the increasing value function theorem. Trying to show this first bullet point. I'm implicitly assuming everything in the first paragraph, including the fact that I'm assuming g prime is less than or equal to h prime. And I'm also now going to assume what's in red here, g of a equals h of a. How do you do it? It's once again a trick. Okay? Define a new function, and we're hoping we can apply the increasing function theorem to that function. F of x equals h of x minus g of x. Why did I do it that way? Because, well, then f prime will be h prime minus g prime. I'm assuming g prime is less than or equal to h prime, so h prime minus g prime will be greater than or equal to 0. And f will be increasing, and I hope that finishes it. This is a slightly modified form of the IFT because I'm not going to show f prime is strictly positive, just greater than or equal to 0. Which means the graph of that won't necessarily be strictly increasing. It could be constant for a while, for example, then go up again. Or even it could be constant the whole time. That could happen. So take the derivative. Linearity implies that f prime of x is h prime of x minus g prime of x, which, again, by the assumption in the very first paragraph, that's always greater than or equal to 0. By the IFT, in modified form, f is increasing. Notice I did not put the word strictly in. Increasing actually includes constant. The book calls it non-decreasing, which is maybe a better way to say it, but also could be confusing. Non-decreasing is the same as increasing, which could include constant, or going up and then constant for a while before you go up again. It could include those cases. I'm hoping the fact that f is increasing will help me finish. Maybe that would be equivalent to this being true. So work it out. What does it mean that f is increasing? That means, in particular, since f of a equals h of a minus g of a is 0, it follows that f of x must be 0, greater than or equal to 0 for all x. F is either going up or it's constant sometimes. If it's starting at 0, this is not the picture anymore, but if f is starting at a value of 0 and its derivative is always greater than or equal to 0, then it could be constant for a while, then go up, then constant for a while, then go up. And there's lots of things that could happen. But it's certainly never negative. It's certainly always greater than or equal to 0, and that essentially does it. That means g of x is less than or equal to h of x because of the formula for f. If that thing right there is always greater than or equal to 0, then you've got a bigger number minus a smaller number. Or they could be equal. G has to be smaller than h for all x. Okay, so again, I'll mention it once more. Maybe this will be the last time. These things are tricky, subtle. I wouldn't expect you to be able to prove them from scratch on your own on the exam. But I do want you to gain skill in logical thinking, so again, I might give you an exam problem where I write out the proof with blanks and you fill in the blanks, or maybe you give reasons for it. Like this was by the IFT, for example. I could say, this means f is increasing, and you give a reason. Oh, it's the increasing function theorem. I start to remember names of these things too. Not necessarily the abbreviations. The racetrack principle is useful. Oops. For proving other things, okay? A theorem is valuable to a mathematician if it can be used to prove a lot of other theorems, because what mathematicians care about are theorems and proofs. That's what pure mathematicians care about. Okay? And those theorems and proofs, they are useful in the real world, as we've seen. We've seen plenty of applications of these things to test so we know we have extreme values that are maximum or minimum, for example. Some theory is going to be helpful for knowing the fundamental theorem of calculus is true as well. Inequalities are useful. Here's an example of an inequality. Where is this kind of thing useful? To me, the most common place this kind of thing comes up as something useful is in a subject called numerical analysis, where you're developing computer methods, algorithms, for doing various things in math, like estimating roots, for example, Newton's method. And you want to know that your method works, or works to a certain degree of accuracy, or works to a certain speed. If you're a computer science major, you'll be learning about algorithm analysis, algorithm construction and analysis in later years. And inequalities are helpful for understanding how well and how fast algorithms work, including inequalities like this. We are going to prove this, but it is something you can pretty easily believe by drawing a picture. The graph of square root of 1 plus x, square root of 1 plus x, looks about like this. And the graph of 1 plus 1/2 x looks about like this. So in fact, this inequality is true for all x greater than or equal to -1. I chose 0 here just because it makes it a little shorter. I could also prove it's true when x is between -1 and 0, too, as you can see in the picture. This right here would be -1 is the boundary of the domain of square root of 1 plus x. And this intercept right there would be -2. This is going to be a 1 here. The most convenient way to do this is with Racetrack Principle. Define a g and an h function, your two horses. What's the idea? I can see it looks like from the calculator or from Mathematica that the graph of g of x is definitely below the graph of h of x when x is greater than or equal to 0. In fact, it looks like the slope, the derivative of g, is less than or equal to the derivative of h. We should verify that. As far as dealing with the a and b, it's a little funny. I'm just going to start by assuming b is positive. The a is going to be 0. That's where those two graphs touch each other. That's the starting moment in time, and they're at the same position at the same moment in time. If I can show g of b is less than or equal to h of b, I'm going to be done. Okay, the fact that b is arbitrary. Don't let the fact that I'm using a different letter of b bother you. It will imply that that's true for all x greater than or equal to 0. Okay? Don't let the different letter bother you. It's an arbitrary number. It doesn't matter what letter you use. You need to understand the idea. That's the important thing. I'm going to let a be 0. Note that these things, these two functions, both have a value of 1 when a is 0. So a is 0 here. B is some arbitrary positive number. If I can show g of b is less than or equal to h of b, where b is an arbitrary positive number, then g will always be less than h, because b is arbitrary. Now I just have to essentially apply the Racetrack Principle. We do need to verify the derivative condition, though. The derivative, well, they're continuous and differentiable as well. The derivative of g is this, and the derivative of h is that, a constant, because h is a linear function. Is g prime always less than or equal to h prime? Yeah, though you should give a little reason. And the little reason is, when x is greater than or equal to 0, this thing that you're dividing by here is bigger than or equal to 1. And that should be pretty clear. If I plug in a number bigger than 0 there, I'm going to get the square root of a number bigger than 1. It's going to be bigger than 1. If I plug in x equals 0, then it's actually equal to 1, so I have the word greater than or equal to here. But yeah, if you plug in x is any number bigger than 0, you're doing the square root of something bigger than 1. It will be bigger than 1. And how's that helpful? I'm essentially taking 1/2 and dividing by something bigger than 1. Yeah, I couldn't put the 2 up on the top there as a 1/2 if I wanted to. Essentially, I've got 1/2 divided by something bigger than 1. If you divide by something bigger than 1, divide a positive number by something bigger than 1, it gets smaller. Smaller than 1/2 in this case. Right? If this were square root were 1.2, 2 times 1.2 is 2.4. 1 divided by 2.4 is less than 1/2. You can try numbers if you aren't quite believing it in terms of the symbols. Now apply the racetrack principle to say G is always less than or equal to H. In particular, G of B is less than or equal to H of B. We're done. Praise the Lord. Okay? So these things they're tricky. They're subtle. The most difficult thing is just knowing what to do. Trying to make it easier on you. I just want you to understand based on reading, not necessarily come at it from scratch and be able to prove from scratch. Kind of like in geometry in high school, right? For a lot of the time, you just have to give reasons for the steps. Maybe sometimes you have to come up with the steps in easier examples. But sometimes you just have to give reasons. But I like to emphasize that proofs are arguments. They should be written in sentences. You're trying to explain something to somebody. Give reasons for them using deductive logic. By the way, this is useful. This kind of thing is useful outside of math. If you become a lawyer, you want to be able to use deductive logic in your arguments to the court, to the judge or the jury. Okay? Or if you're in business, you want to be able to justify to your manager why you should spend money on some new equipment, you better be able to use deductive logic. You've got some assumptions, you've got some things that you think are true, you can use those things in logic to reach some conclusion. How are we doing in time? Okay, again, we are trying for just one lecture today, and I'm aiming to end 5 to 10 minutes early. So I'm aiming to end in the next 30 to 35 minutes here. Maybe stretch a little bit. We're going back to motion now, transitioning from the theory to the parametric equations and curves of motion, and then also the fundamental theorem of calculus in the context of this stuff. We will come back to that after Thanksgiving as well. And we'll also talk about some new applications, fluid flow and data modeling. Those are our final 2 applications. Here's a non-uniform motion. Non-uniform meaning non-constant speed. X is f of t is t, and y is g of t is t to the 3/2 for t going between 0 and 4. Why am I doing an example with 3/2 power? Because it makes the calculation of the distance function, the distance traveled function, possible to do. It's not simple, but it's possible. That's why I'm using the 3/2. If I use other exponents, it can sometimes be very difficult to find the distance traveled function. That's my underlying reason for using kind of a strange example. Imagine plotting this. And maybe you don't even have a graphing calculator. Of course, if you do have a graphing calculator, you should be able to plot it in parametric coordinate calculator. I shared that video with you. You should make sure you can do that. That's something you should be able to do for the 3rd exam and also the final exam. But if you didn't have a calculator that was graphing calculator, could you still plot? Yeah, just plot points essentially. Make a table of values. There's a big table. Don't write those numbers down. It won't take too long. But just think about it briefly with me. X equals t. So no matter what t is here, notice the first coordinate of these points is equal to t, because x equals t. So the rightward velocity, so to speak, of the curve is going to be constant. The velocity in the horizontal direction. On the other hand, y is not increasing at a constant rate, and it's not equal to t. It's equal to t to the 3/2. So evidently 0.25 to the 3/2 is about 0.13. 0.5 to the 3/2 is about 0.35. These are approximations, by the way. I'm rounding 2 places after the decimal. 1 to the 3/2 is 1. 4 to the 3/2 is exactly 8, because we're raising something to the 3/2 power. 8 to the 3/2 means the square root of 8 quantity, oops, 4, sorry. I knew that didn't make sense. 4 to the 3 halves is the square root of 4 quantity cubed. 2 cubed is 8. You can also think of it the other way. You can think of it as the square root of 4 cubed. 4 cubed is 64. You get the same answer either way. Now just plot those points. Here they are in an xy plane. 0, 0 at the start. This point here is 0.25, 0.13. Then 0.5, 0.35, etc. This last point is 4, 8, when t is 4. This is supposed to represent a motion. You need to use your imagination. Imagine a bug walking and being at this point after a quarter second, this point after a half second, this point after 3/4 of a second, this point after 1 second, etc. The bug is speeding up. It's at this point when 4 seconds have elapsed. The distance between these dots is getting bigger and bigger. That indicates the bug is speeding up. The speed function is not a constant function. This is non-uniform. On the next slide, I'm about to show you a bunch of equations that you are, in part, just trusting. Okay? Though I will try to give you some intuitive reasons for them. I would like to find the speed as a function of t. I'd like to find the distance traveled as a function of t. That's my goal. That's the next slide. What is the speed? What is the distance? The instantaneous speed at any moment in time is a certain function. It's an instantaneous speed, not an average speed. An instantaneous speed at any moment in time. I can plug in the value t and get the speed in centimeters per second or whatever at that moment in time. Here's the formula. You're just trusting the units. The speed as a function of time in general is the square root of dx dt squared plus dy dt squared, which is the same as the square root of f prime of t squared plus g prime of t squared, which for this example is what you see. Again, for this example, f of t is t, g of t is t to the 3 halves power. So f prime of t is 1, and g prime of t is 3 halves t to the 1 half. 3 halves times the square root of t. And that means I made a mistake, actually. Yeah, there's a typo in there. This should be 3 halves t to the 1 half. But the final answer is right. Okay? 3 halves to the square root of 9/4. T to the 1 half squared is t. I am assuming t is greater than or equal to 0. So again, there's a typo right there. I'll fix it before it comes down or on the shirt drive. Does this make intuitive sense that the speed should be this? Well, we are going to talk a little bit about vectors next week. It's not going to be a huge point of emphasis for us, but we will talk about it some. If you know about vectors in physics, there are things called velocity vectors. Velocity vectors are arrows that point in the direction of motion and have a length equal to the speed. And they have what are called horizontal and vertical components. Left-right components, up-down components. You can break this down into the sum of a horizontal vector and a vertical vector. It's a right triangle there. Those derivatives that are on the slide are not really the lengths of these components, but their length with a direction. I made these so these are both positive. But if the arrow is going down like this, then dx dt, if I label this side with dx dt here, it's actually representing a negative quantity. A negative derivative, because it's going left-handed. X is decreasing. And dy dt here would be negative as well. So even though I'm labeling these as if they are lengths, they're not really lengths. They're absolute values of the lengths, but they can be negative. These are called, again, the horizontal and vertical components of velocity, of the velocity vector. And you think about the Pythagorean theorem, the length of this side here is going to be the square root of dx dt squared plus dy dt squared. That'll be the actual length of that side in either case. The length is that. That can't be negative. This length as a positive quantity is still the same thing. So that's some intuition behind why that's the right formula for the speed. It's really the length of the velocity vector. The Pythagorean theorem. The distance traveled will be the single unique antiderivative of this function that passes through the origin. Dist of 0 better be 0. At time 0, you haven't traveled any distance. Remember, there are infinitely many antiderivatives. Plus c can be arbitrary. We only want one particular one. Notationally, we use this definite integral. You can write that. Indefinite integrals are antiderivatives. They are indefinite. They can be infinitely many things. Plus c can be anything. Definite integrals are not infinitely many things. They're just one quantity. That's why they are definite as opposed to indefinite. You have limits of integration at home, a 0 and a t in this case. When you look at this equation, you should, in your mind, think of t as fixed, a fixed positive number. I am integrating the speed function over some interval from 0 to t. U is, again, just a dummy variable, a common letter used in this situation. W could be used. A Greek letter I like using a lot here is tau, because it's the Greek version of t. It doesn't matter what you call it, okay? I just need some other letter, is the point. If this is the speed curve, and this is some fixed instant in time, this integral represents the area under the curve. That's the main conceptual point. In fact, that is the fundamental theorem of calculus that equals the area under the curve. We are approaching this a little bit backwards, in a sense, compared to many calculus classes. Many calculus classes start this content by talking about estimating areas with rectangles. They're called Riemann sums, and then letting the number of rectangles go to infinity. And we will talk about that Friday of next week, maybe. Before they start talking about them as representing areas necessarily, although, I mean, they're kind of talking about areas there anyway. Before they start talking about having arbitrary numbers up here. I'm doing it the reverse. I think this is a better way to do it. I'm starting with the idea of an integral as being an area, and then later on we'll go ahead and approximate it with rectangles when we need to. Approximate the area. I'm approaching it more like a scientist or engineer would, not a mathematician. A mathematician would start with those summations and let the number of rectangles go to infinity, take a limit. But I think conceptually it's better to go this way. Anyway, so we gotta find this antiderivative. Are you kidding me? Is it really possible to do? Yes. How? Guessing and checking. I'm serious. Guessing and checking. What? We're after an antiderivative of this function. If this were just a plain u to the 1/2, you already know the answer. Let me call it w to the 1/2. If there were just a plain w to the 1/2 here, through a bit of guessing and checking, be the answer for the indefinite interval at least, I know the answer's got to have a 3/2 power. Because when you differentiate this, you get w to the 1/2, right? Bring the 3/2 down in front. 3/2 times 2/3 is 1. Subtract 1 from this exponent, you get w to the 1/2. The derivative of c is 0. You can always check this kind of thing by differentiating. So whatever I guess, it's probably going to involve this expression to the 3/2 power. And some expression like that to the 3/2 power, if I differentiate it, I'll need the chain rule. I'll get this extra factor of 9/4 coming into play. The derivative of the inside function. So, I'm not telling you more details than that, other than just to say this is the answer. But you can check it. Take some experimentation, okay? This is not something that's easy to do. You got to experiment a little bit, but once you've got the answer, you can check it. You might also be wondering why I subtract this 8/27 as well, that constant, and that is to make sure the graph goes through the origin. Pick one particular antiderivative. You can check it. Take the derivative with respect to t. I won't bother with the constant. I'll just focus on the. Let's see. I'll just focus on this part right here. 8/27, 1 plus 9/4 t to the 3/2 power. Differentiate that. Bring down the 3/2. Subtract 1 from that exponent. Then don't forget from the chain rule, multiply times the derivative of the inside function. The derivative of 1 plus 9/4 t with respect to t is 9/4. Simplify. What does that simplify to? Well, the 3 cancels with the 27 to leave a 3 there. The 2 cancels with the 8 to leave a 4 there. Excuse me, mistake, that's a 9. This simplifies to 4 9ths. Hey, 4 9ths and 9/4 cancel. 1. I get my speed function. Guessing and checking is the way to go. Yes, I'm not lying. Guessing and checking and experience does help. Knowledge does help. Factual information about derivatives. And basic kinds of integrals like that. There. Yeah, and I subtracted the 8/27 there, and I also factored it out to make sure the graph goes to the origin. Look at this final form. When you plug in t equals 0, you get 1 to the plus 0, 1 to the 3/2 is 1. 1 minus 1 is 0. 0 times 8/27 is 0. That makes sure the graph goes through the origin. This is the one particular antiderivative that I want. I don't want a plus c there. I don't want c to be 0. I want it to be minus 8/27. So when I write this way. So it's not a simple function, but it can be found, and it can be graphed. Oh, by the way, I do have an animation of the earlier example. Zooming in to the origin, this was the example from earlier. To see that blue curve especially, you do keep getting more and more tiny oscillations the further you go in. They just get harder and harder to see. But the graph does look like more and more like a straight line as well. Those two things are not contradicting each other. Looks like it's increasing, but it's not. It's increasing overall, you might say, but there are plenty of ups and downs. They're just little. The example we're doing here is this one here. Actually, I don't have an animation for this one, but here's how I made the original graph. I'll save this, and you can use this kind of code if you want to. Again, don't be afraid to experiment with the Mathematica code, which does remind me I need to find some videos that might give help to you as well. I should do that this afternoon, as well as running your online quiz. Our final main example today is a motion defined by polynomial parametric equations. Next week we'll do a realistic example of projectile motion as well. Maybe both with and without air resistance, and see what happens. This is not a projectile motion. It's just a bug traveling on a piece of paper, or maybe a car traveling on the road. This time x equals f of t is going to be t squared. G of t is going to be t cubed minus t. Once again, if you didn't have a graphing calculator, you'd want to plot points. Notice that I'm starting t at -2 here instead of 0. Why am I doing that? Partially just because I can if I want. And partially because it makes the picture a little prettier. It makes it symmetric. Okay. So here are the values that I picked from -2 to +2. Notice that the x-coordinate is the square of t. X equals t squared, so -2 squared is +4. +2 squared is also +4. -1.5 squared, I hope you have memorized. Maybe it is +2.25, because 15 squared is 225. That's the reason. +1.5 squared is 2.25. So the x-coordinate is t squared. The y-coordinate is a bit more complicated. T cubed minus t. Let's just check that for t equals -2. -2 cubed is going to be -8. Minus -2 is -8. Plus 2 is -6. When t is +2, I get 2 cubed minus 2. 8 minus 2 is +6. And you can check the other values. And again, I'm rounding to 2 places after the decimal. And here's the picture. Nice symmetric picture. The motion starts right there when t is -2. Kind of a big distance there from t equals 0 to t equals 0.25. The bug is, or the car, say, is moving pretty quickly there. But then these dots get closer and closer together. The car or bug is slowing down. It's at this point, 1, 0, look, when t is -1. And then it does a loop-the-loop, going fairly slow, goes to the origin when t is 0, back to this point when t is +1, and then speeds up as it heads toward t equals 2. Is it a problem if this fails the vertical line test? No, it's not. You're right. Good guess. Why is it not a problem? Because we're not graphing y as a function of x here. We're graphing x and y as functions of t together in one picture. It's a different kind of thing. It doesn't matter that it fails the vertical line test. If I were to graph this thing as a function of x, it would really be two functions of x. This piece here and this piece there. They'd be reflections of each other across the x-axis. All right, what's the speed? What's the distance? The instantaneous speed at any moment is the same function as before as far as the abstract form, though the details are different. We get a different final answer. On the board here. F of t is t squared. G of t is t cubed minus t. Just mentally check. The derivative of f is 2t. The derivative of g is 3t squared minus 1. And squaring those things, I skipped a few steps there. In the simplifying, you can fill in the details. You get the square root of 1 minus 2t squared plus 9t over 4. It's a function of t. It's not a constant speed. It's a non-uniform speed. We can graph this to see this change. We will. How about the distance? This time, since time is not starting at 0 but -2, I don't want dist of 0 to be 0. I want dist of -2 to be 0. Time is starting at -2. Partially just because I want to, and partially because it makes a prettier picture. Mostly just because I want to. Just feel like it. It's okay. It's most natural to start t at 0, but I can start at other places. In fact, there are even times where you can situations where you might want to start time at minus infinity. Really? Minus infinity? Maybe. We can write the same kind of thing for the distance in definite interval notation. Notice the lower limit of integration there, that's what it's called, is no longer 0, it's -2. The upper limit is your variable. Again, I'm using a u, I can use any other letter besides d and t that I want. The fundamental theorem of calculus that we talked about says this will be an antiderivative. Right? We wrote that down last time. You had a few homework problems about it. You probably looked at the answer in the back because you weren't sure what to do. Okay? But it's actually very easy to do it. Whenever you've got a situation where you take the derivative of an integral like this, and now I'm using x as the variable, and the bottom can be any number whatsoever. It doesn't matter. -3, +7, pi. It doesn't matter. Here I'm using t as the dummy variable. The answer is the function you're integrating. That's a very profound thing, and it's true. And get the letters right. Make your true variable you're differentiating with respect to the upper limit of the integral, and also put it there. Don't put an f of t there. We want to differentiate this function of x. This is a function of x, not t. This whole expression. It's the area under the graph of f, if the graph is above the axis at least, between pi and some value of x. This is the area under the speed graph, where u goes between -2 and some arbitrary positive number, or arbitrary number t bigger than -2. Though actually you can plug in t equals -2 here, and you'd be finding the area under the graph above -2. Yeah, that's just a line. It has no area. The area is 0. Integrating from -2 to 2, -2 to -2, excuse me, gives you 0 because there's no area. Finding the area of a line. Now, lines have no area. 0. That equals 0 there. Okay, but again, this begs a question. How do you actually figure out the answer? Can we simplify this? Can we get rid of the integral? We could in the last slide, the last example, 2 slides ago, by guessing. Is it possible to guess here? Can this be simple? Not by mere mortals. So does that mean God can simplify it? Yes. Does it mean any human can simplify it? Really smart people. That's not me. I had Mathematica do it. There's the answer. I had Mathematica do the integral. There it is. Woohoo! Isn't that beautiful? Have any idea what that means? Do I have any idea what it means? Well, a little bit. I do see, what, imaginary numbers in there? Yeah, though the imaginary number will somehow cancel in the end. You will get a real quantity. What, elliptic E and elliptic F? What's that? Arc cinch? Is that H supposed to be there? Yeah, it actually is. It's not arc sine, it's arc cinch. Did you read about hyperbolic functions way back when? We didn't talk about it in class, but that's an inverse hyperbolic function. Yikes! You see why no mere mortal can do it? Or just super genius? But that doesn't matter. We can still plug it into Mathematica. And we can still evaluate its value at t equals 0 there. That's what I did here. That's not obvious, but that's what I did actually, is I evaluated it at t equals 0. And I get about -8.1 minus 4.44 times 10 to the -16i. Or that's a 0 actually. That's computer error. Notice the large negative exponent. That's computer error. It's not supposed to be. This is the actual approximation. Which means if I want this graph to go to the right point, actually I didn't plug in t equals 0, I plugged in t equals -2. You have to add the 8.10284 to it at the end there. And now you can plot. And there's the graph of the distance traveled in blue and the speed in red. And the graphs are not that out of the ordinary looking. The blue graph is the one that has the crazy formula. The red graph's formula is a lot simpler. But this should make sense. Look at this. Blue's distance traveled. I start off with kind of a large speed here at first. The slope is pretty large. The red value is pretty large. This is concave down. I'm slowing down. This graph, the speed is going down. Looks like I have an inflection point there where the graph changes from concave down to concave up. Is that really the case? Or maybe it's the opposite way. What's going on here with the speed? Is it constant or just, is there a min? It's pretty subtle actually. There's actually a local max at t equals 0 and a local min here and here. These 2 points are ever so slightly lower than that point. So actually, you slow down, slow down, slow down, then you speed up ever so slowly before slowing down again ever so slowly, before speeding up again fast. You can think about this in terms of areas. Don't worry about the meaning of this code. B is the right endpoint. It's time, effectively. Now, my computer, this line right here is not dashed. I don't know why they dashed on this. Both. Mine. Anyway, slow this down and think about it. What do we have going on here? This is really important. The blue graph is the distance traveled. The red graph is the speed. This pink dot there is the actual motion. It's like the object's moving on this vertical axis here. It's going kind of slow there. Speed it up a little more. Then it speeds up as this line gets steeper and the value of the speed goes higher. Starts pretty fast, slows down. Then starts to speed up again. Now, that's the actual motion on the vertical axis. The dot on the horizontal axis is just time going by at a constant speed. That's what time does, unless you bring relativity into account. No relativity here. The slope of the blue is the value of the red. If you look at the slope of this tangent line here, its slope is always the second coordinate of that point. And the accumulated area under the speed, under the red graph in light blue here that you can see better than last time, that is the value of the blue graph. I'm accumulating areas. At any stopping point, say right here, the area under this red graph right there is the second coordinate of this point in the blue graph. The antiderivative, the integral, is giving you the area. You can interpret the values of the blue graph as areas in the red graph, the values of the distance as areas with the speed. You got to think about this over and over again. In fact, put this in the shared folder. You can share it with your parents. Mom and Dad, can you tell me what's going on here? And they probably won't be able to. And so you work at trying to tell them what's going on. Okay, it'll be helpful for you. Now you may not get it right first try, but keep trying. Almost done here. No baby announcement, sorry to say. Mathematica can do it, though, in a funny way. The funny way is the way with the elliptic F and the elliptic E and the arcsinh and the I's in there. It makes me impressed by Mathematica. It can do it. I think we can still make graphs like I just showed you. Actually, I do have one more slide. I think it's worth going over in about 1 minute, and then I'll let you go. We might want to answer these kinds of questions. We can determine the local extreme points of the speed and the inflection points of the distance by using methods from chapter 4 at the beginning, optimization, find critical points, use the first and second derivative test. Here's a slide with the details. I'm going to square the speed, because if I can minimize or maximize the square of the speed, that'll minimize or maximize the speed itself, and I can avoid square roots. Take the derivative, set it equal to 0, solve for t. Critical points are 3 of them, 0 and plus or minus 1/3. The plus or minus 1/3 are those two low points. The 0 is in the middle. That's the slight local maximum. Not a global maximum. Graph goes higher, but a local maximum at t equals 0. You have to use the first or second derivative test to verify it. I'm not going to take the time to do that. There is a local max at t equals 0 and local min at t is plus or minus 1/3. The local max value turns out to be 1. The local min value at both of those critical points is the same thing, 2 square root of 2 over 3, which is about 2.94. Okay, so you should check that while you're eating your turkey, and then show them the picture. Check my work. I'll let you know when I hear about the baby, okay, over email. We didn't get a viral moment on the video, all right? But thanks for being here. Have a good Thanksgiving.